Okay, so thank you very much for being here. And today I'm going to talk about mainly what I did during my PhD, so a long time ago, which is, like, as you can see from the title, like using quantum memories in the quantum networks. So how can we reach higher distances, long distances, and improve the performance. Okay, so let's start. It won't work. Okay, so yes, the introduction. So I'm going to talk about QKD, and then I will describe this type of protocol, which is MDI QKD. Maybe many of you guys already know. It's a very old protocol, and then how we can improve this protocol using memories. And then I will show different type of implementation, let's say, although we never did any experiments, they're just simulations. Okay, so yes, the introduction, I think already you guys, after these 2 weeks, know what are the advantages of using quantum networks. These are like listed the 3 advantages or three improvements compared to classical networks, let's say, that could, for example, when we use quantum networks for quantum computation, so distributing qubit, this could enhance the computational power of quantum computers. Then we can use also quantum networks, so the distributing qubit or entangled state for communication. And this could be, the advantage in this case is, for example, when you apply QKD or quantum key distribution, and in this way the security could be higher. And then also quantum network for sensing, so will increase the, let's say, the precision of measurements. So the right side of this slide, you can see already there have been some implementation of the very small networks, actually. So, for example, the Tokyo QKD network, and then you have it like in China. Yeah, these 2,000 kilometers, I think, connecting Beijing to Shanghai. Also in Europe, India, and basically everywhere on the world. So this is just to show you that like there is a very big interest in implementing this type of technology. Okay, so in particular in my talk, I'm going to speak QKD. Again, just attending to some of the previous talks, I noticed like there already been an introduction of QKD. So, but like I want to say again something, otherwise I will be too short. So the thing I'm going to talk today is memory-assisted measurement device-independent quantum key distribution. So I will address each of these single 3 words, such way you can understand what I'm talking about. So let's start with from the end. So quantum key distribution. So what is quantum key distribution? And so let me show you the motivation why we need quantum key distribution. So the thing is, like today, the way we communicate in a secure way is based on the so-called public key cryptography. Maybe the next speaker will say something about that. But anyway, so it's the way you can communicate in, I guess, on WhatsApp or anyway, with in a secure way. And this is the security of public key cryptography. One of the protocols, let's say, that implement this type of cryptography is the RSA protocol. The thing is like, yeah, so that's actually the way it works. So you have a public key and a private key. And the way these 2 keys are connected is basically like with an algorithm. And the security, so the important thing to remember here is that the security of this protocol relies on the computational power. So if you have a very big computer, in theory, you can break this code, but it's going to take a really long time to break it. So the thing is like that quantum computers, on the other hand, might break this type of cryptography in a reasonable short time. Okay, so, and quantum computer is an existing reality, right? Maybe 10 years or 20 years ago, they were not still, you know, like very evolved, they were not that good, but, you know, with the recent advancement in the technology, we can make today quantum computers with a few hundred qubits, and therefore, this scenario can actually happen, okay? So if this scenario happens, this type of cryptography will be useless, right? The security will be compromised. And as I say, quantum computer is an existing reality. So this is me and a quantum computer in Tokyo. Okay, so yeah, so it's something that exists, okay? So we want to address this issue. And now there is, that's the motivation why, you know, like QKD, in the last 15 years, as always, the interest towards QKD has been increased because, as I say, the RSA protocol relies on the computational power to, the security of this protocol relies on the computational power. On the other hand, the QKD, the security, at least in theory, relies only on the laws of quantum mechanics. So as long as these laws are valid, QKD will be good to do the job of encrypting data and have a secure communication. Okay, so you have, I guess, I think you guys already know, but I want to say it again. So also, you know, as you can see, we have Alice and Bob and Eve. I think they're very cute, these images, and I want to acknowledge Stephen for finding these cute pictures of Alice and Bob, because my previous pictures, he said they were really boring. So anyway, and so let's see how it works. So you have Alice want to send a message to Bob, and she uses a secret key to encode her message, which is basically a string of bits. And then this key is sent this message, this encrypted message is sent to Bob, and Bob used exactly the same key. Okay, the same key is used to decode the message. So, of course, you know, like Alice and Bob must have the same key, right? In such a way they could, communicate in a secure way. So the QKD is basically a secure way of distributing this key. Okay, this is a string of bits. So yes, that's the main concept behind QKD. And just this sentence, I just put it here because you will see that it's quite important. The main way, okay, so you have this QKD, okay, we are happy now, and how to evaluate, okay, the performance of this of a QKD protocol, you need to find the rate. Okay, so Alice and Bob want to communicate, but of course it will be useless to communicate, let's say, to exchanging a key bit, 1 key bit per hour or per day. So the rate, so how fast Alice and Bob can exchange this key is the main figure of merit for QKD. Okay, it's the main figure of merit, and I will show you in the next slide how we can calculate and in different protocols. Okay, so let me go on. I addressed the QKD. Okay, so the QKD, we did it. So let's go to the other one, which is measurement device independent, okay? Measurement device independent is a protocol that was made, let's say, in 2012. This is the main paper, and so measurement device independent is a QKD protocol, and so the goal is to find a key and then to share a key between Alice and Bob. And why it's called measurement device independent? Because basically the way it works. This is the main. I took this picture from the paper, but then I'll show you in the next slide a better representation. The name is due to the fact that the thing is like the QKD, as I say, it's super secure, it's ultra secure. Okay, but when you implement a QKD protocol, there could be many challenges, and also there are many, like imperfections of the devices that you are using. So, for example, you have imperfection in your sources emitting the state, or imperfection in the measurement devices. And Eve, you remember Eve was the eavesdropper in the middle. the eavesdropper can exploit this imperfection in inefficiencies of the devices to extract some information of the key. Okay, so she can use this information, and in this way, the implementation will not be secure anymore. So, okay, these guys, so one of the type of attacks that Eve can do is attacks on the measurement devices, which are photon detectors. And so these guys came out with ideas and say, you know what, rather than giving the photon detectors, the measurement device to Alice and Bob, why don't we give it to independent, to an untrusted station? And that's the main idea behind it. Okay, so in this case, as you can see, you have, for example, Alice and Bob, and then they send their state to a middle station, ideally in the middle of them, and then the middle guy, which normally is called Charlie, which is completely untrusted. Okay, we don't have to trust this guy. We'll make a type of measurement, which is called Bell state measurement, and based on the outcome, he will tell Alice and Bob basically what he got. Okay, I know it's a bit confusing, but I'm going to explain better in the next slide. Here, what is important of this type of protocol is that in this case, we don't have to care about the measurement device anymore. Okay, so for the security of the protocol. That's the main, let's say, the new thing coming from this type of QKD protocol. So let me show you how measurement device independent QKD works, this type of protocol. So as you can see, you have still this cute Alice and Bob. They're separated by some distance L, and ideally we put Charlie in the middle, where is the red box, where this type of measurement that I call BSM is a Bell state measurement. So basically it will project, actually it's a partial state measurement in the sense that, we have 4 Bell states, and this type of measurement is performed using linear optical elements, like, for example, beam splitter. So by doing this measurement, we can distinguish only 2 of the 4 Bell states. And anyway, these are just details. The way it works, the way you have to think about it is just that when Alice and Bob send their state to this Bell state measurement, this measurement creates some correlation between these 2 states, okay? So, and this correlation is used to extract the key. So, yeah, you can see that's the state. And another thing that we can, the way we could implement this protocol is, for example, using, so as you know already, maybe some of the previous speakers already introduced, the fact that in QKD, normally we use Alice and Bob, right? They use 2 bases, the X basis and the Z basis, okay? And for example, in the Z basis, you have 2 states, 0, 1, and the X basis also you have 2 states, and they correspond to actual bits. Okay, so for example, the 0 state is the bit 0, and the 1 state is the bit 1, and in the X basis, plus correspond to bit 0 and minus to bit 1. Okay, so that's basically the way we could encode the bit into these spaces. And then, as I showed you before, Alice and Bob use the photons to encode this bit. Okay, so that's the main, the carrier of the information. Okay, so the information which is encoded in this, the bit is encoded, is carried by photons. And of course, the photons might have, as you already know, different degrees of freedom. I'm gonna just put 2 here, but there are many, of course, but for example, polarization. So you have, in this case, polarization, as you can see here, is H and V correspond to the Z basis, and plus 45, minus 45 to the X basis. So in that case, H photon will be bit 0, and V photon will be bit 1. Okay, so to make things, there are many different types of encoding. You can use phase encoding, time beam encoding. I think already you guys are expert on that. And then also another way you can do it is so-called space encoding. So if you have, let's say, 2 spatial modes, you can consider H as 1, 0. So 1 is, for example, means 1 photon in the upper mode and 0 photon in the lower mode. And then, or 0, 1. That's another type of encoding that I will use in the next slides. That's why I put it here. As you can see, they are perfectly the same. Okay, so you can write H as a 1, 0, B as a 0, 1, and of course, plus 45 and minus 45 will be the X basis encoding. So, yes, this is the beam splitter. So, as I say, the way this type of measurement, the type of the best state measurement is performed is using a beam splitter. But again, I think yesterday, Professor Beauregard already talked a lot about beam splitters. Here, I just want to show you what we, like the input-output relationship that we need for this type of protocol. So we have a 50-50 beam splitter, so a specific type of beam splitter, and which is basically a mirror. So when you send a photon, for example, here in this mode A, the photon could be transmitted or it could be reflected, and you get, for example, 1, 0 will be transformed like that. So with 50% probability in one mode, 50% in the other one. And the other type of interaction that we will need is this type of interaction. When you have two photons, what happens is actually you never have that the photons will come out each for one mode, but you have that either two will go, so either both will be reflected or both will be transmitted. So when you have, let's say, the 1-1 state, the 1-1, that means you have one photon in A mode and in B mode, the outcome will be that one, okay? And that's all what we need. So we have two photons in A prime mode or two photons in the B prime mode with 50% probability. And that's all we need to do the simulation for the QKD, basically. That's all so we don't need more than other type of relations of the beam splitter. Okay, so how do we know that we have, that the state sent by Alice Bob are correlated? So we have to define a successful event. Okay, so as I said, Alice and Bob are sending the state to the middle station, and this type of encoding is the so-called the spatial encoding. Okay, so as you can see, we have the upper mode and the lower mode on both sides of Alice and Bob. So the successful event in the Z basis, okay, because we have actually in all bases, even in the X basis and the Z basis, is given by when Alice and Bob send their states, and you get a click on the upper detectors and one click in the lower detectors. Okay, so that's the successful event. And then again, so for example, they can send more states. So the event 1 was successful because we have one click there and one click on the lower part, and also event 2 is also successful. Okay, so that's the way we define successful events. You might wonder, okay, but what about Charlie? You know, we have to assume there is a guy in the middle that might know something about the key, because of course he's there. Also, you can see that, as I said, this node is completely untrusted, the middle node, right? And the thing is, like, as you can see in this this type of measurement, we have this 50-50 beam splitter, right? So as I show you here, for example, I show you again. So they send here. Okay, so this 50-50 beam splitter, the reason we put this 50-50 beam splitter is because we want to, let's say, get rid of the information from where the photon arrived. Okay, so as I said, for example, if you, let me use this. Okay, so when the photon, for example, in that case, right, is going here, when it meet this, interfere with this, the beam splitter, right, it can go either here or there. The same on this side, can go on both detectors. But of course, after the 50-50 beam splitter, what Charlie can see only is the detection event. Okay, so you can see, for example, this detector click or this other detector click. But of course, he doesn't know whether this click come from a photon, is due to the photon coming from Alice or from Bob. So that's the reason why we put this 50-50 beam splitter here. basically wash away the information from where the photons arrived. Of course, as you can see here, these events are completely symmetric, as you can see, right? You have this one and this one, both are successful. And of course, Alice and Bob knows which photon they have been sent. They send, so in this way they can extract the key. Let's say Charlie has 50% of chances to guess it, but if you assume that the key is very, very long, right? It's like many bits. 50% is 1 to the over 2 to the power of the number of bits. So eventually, the probability that Charlie will know all the keys is very, very small. Okay, so that's the successful event. So as I say, the successful event is 1 click here and 1 click in the lower part. The unsuccessful events are instead when you don't get this type of a click pattern. So for example, when they send the same state, so as you can see, they send both, for example, this is a H photon, for example, and Bob also send H photon. So it goes both in this part. So you can see now in this case, we only have 1 click here. Or when they say, for example, so when they basically send the same state in the Z basis. Okay, in the Z basis, you have these unsuccessful click events. And these unsuccessful click events are discarded. So basically, Charlie will say, like I get for this event number 3, I only get a click here. That's what Charlie will say to Alice and Bob. So Alice and Bob will just say, okay, let's not consider, let's throw away event 3. Event 4 also, it was only 1 click here. So again, they will throw away this event. They will not be taken for the evaluation of the key. That's the way basically this MDI-QKD protocol works. Of course, in the X basis is similar. Okay, so the same concept, the same type of game, let's say. So in the X basis, for example, you send a plus or minus, and again, the successful event is a click. 1 click in one of the detectors, another click in the lower detector. So you can actually find this very easy. Okay, so yes, Alice and Bob discarded these events. However, what happened when, so as you can see here, these click patterns are caused by photons, right, arriving on the detectors. But sometimes the photons could be lost. For example, as you can see here, Bob, the photon has disappeared at some point. Show you again. Because these photons travel, as you know, in optical fibers, so there is some attenuation length, and this photon could be leaked out. And so photons don't arrive. And of course, you can say, fine, if this photon don't arrive here, you only have 1 click. And as I said before, this click is not a successful event. So in this case, if this photon is lost, you have only 1 click here, and Charlie will say, I only got 1 click, so discard this event. However, we have some imperfections in our devices. For example, we have some imperfection that they can make things slightly more complicated. For example, as I say that you have in this specific example, this photon sent by Alice reach these detectors, but this photon was lost. So, okay, so you say this detector cannot click. No, actually, maybe many of you know this detector can actually click because there is a phenomenon called dark counts, which is an inefficiency, let's say, a noise in the detectors, the photon detectors. And this dark count is basically the detector will click even if no photons arrive there. So in other words, what we get is that Alice sent her photon, this photon reached these detectors, Bob sent his photon, but this photon has been lost. So if we have a dark count event in one of these two, detectors, we will get a click, right? So in that case, if we get a click, we have a successful event, but this successful event was not coming from a photon sent by Bob. That's the main thing. So what I'm saying here is I'm just describing a way we can have an error, right? So the errors basically, so when let's say the devices in the protocol are not ideal, the noise introduced by inefficiency of the setup can cause errors. Yeah. Well, so anyway, I explained quantum key distribution. Okay, so this was how measurement device independent QKD worked. As I say, the most important thing to remember is that this measurement setup is completely untrusted. Let me go to the last part, which is the memory assisted. Okay. Okay, so distance of relevant bulb, right? I showed you before that the fact that the photon sent by bulb was lost, this can cause some problems in the evaluation of the key rate, right? And that's it. There's nothing we can do. So you have these nice things traveling, but then at some point you have this photon has been lost, blah blah blah. Yes, I did too many photons. But anyway, so the thing is, like, we know that the way the rate scales with the distance, scales exponentially with the distance. Okay, so the amount of photon reaching bulb scales exponentially with the distance. And this is the main limitation, I think, for long-distance quantum key distribution, right? Long distance, we want to reach, for example, thousands of kilometers, or more than thousands, 10,000 kilometers. Already 100 kilometers, if you just put 100 here, okay, so this should be divided by something else. I'll show you later. Anyway, so what I'm saying is, like, if you put 100, already the rate is already very low. And do you remember what I said before? What's the main figure of merit for QKD? The rate. So if the rate is too low, QKD will be useless, at least for long distances, right? And that's what we want, actually, right? We want to communicate with, I don't know, we want to communicate with other countries normally. And to do that, we need thousands of kilometers. Okay, so the way we address these here is, so one way I probably already found out yesterday was using quantum repeaters, right? So I think Beauregard talked about quantum repeaters a lot. We have this type of, like distribution of entangled states and over short distances. And quantum repeater, at least on Earth, is the best way we can do long distance communication. But quantum repeaters are really demanding. You need many memories, you need very high efficiency memories, quantum memories, and so at the moment we do not have quantum repeaters, although there is a lot of interest in the implementation, but it's very, very challenging. Also, from an implementation point of view, the efficiencies of the quantum memories, the coherence time, the characteristics of these memories must be really good for the implementation of quantum repeater. Okay, so I'm talking about memories, which is the answer to these questions, right? How do we store quantum information? Memories. Of course, I'm not going to say anything because already the previous speaker say many things about memories. The thing only that the concept is that we send a photon, and the photon is stored, and the photon then could be retrieved, which is basically a way to transfer information, if you want. So there is this this is the information encoded in a polarized photon, okay, alpha and beta. Alpha and beta are complex numbers, but it's actually the information, right? It's telling us how much H we have and how much V we have, let's say. And this information, so these numbers, alpha and beta, in a quantum memories, so the job of a quantum memory is basically is to store this information, alpha, beta, in some degree of, some internal degree of freedom. It could be energy level, for example, of these quantum memories, which is an atom. If you think of a two-level atom, the job is to store this information, and then the last part is that we have to retrieve this information. So at the end, we want again the same photon that we send initially. So this is these steps are ideally what a quantum memories must do. But unfortunately, unfortunately, I mean, Fortunately, we have this type of devices. Unfortunately, we do not have, let's say, perfect quantum memories that can do exactly this job. I think Steve said in the previous, we have a lot of inefficiency, like writing efficiency, reading efficiency, coherence time. I'll show you now how these type of noise in the memories could affect the system. But anyway, so that's all you have to remember about memories. So the idea was to use, so again, this is the MDI QKD, okay, Alice and Bob, and Charlie in the middle, performing a Bell set measurement. We put two quantum memories just before the Bell state measurement. That's the idea. Why this is good? Because now, as you can see, they send the photons to the memories, right? And for example, as you can see here, the photon of Bob was lost, but the photon of Alice reached the quantum memory. So now this photon has been stored into the quantum memory, and we wait until the photon sent by Bob reach the other quantum memory. When they reach the other quantum memory, at some point it will reach anyway. When they reach the other quantum memory, so when these two quantum memories are loaded with the state sent by Alice and Bob, these photons could be retrieved like that, and we perform a Bell state measurement. And of course, in this case, the rate, before, without memories was proportional to, was scaling exponentially L with L, and now with L over 2. So that's the L over 2, because now, as you can see, now we only, once this memory, or this memory, of course, just assuming first Alice memory is loaded, we only have to wait for half of the distance, right? So that's why we have this L over 2 scaling. And the reason I say that, so this might look like a quantum repeater in the sense, like you think like, quantum repeater works similarly. We have memories, and also we have a Bell state measurement, and we create this correlation between Alice and Bob. However, the characteristics, the features of the quantum memories used for this type of protocol are not that demanding as the ones of a quantum repeater. So in other words, what I'm trying to say is that if this type of protocol does not work, not even quantum repeater could work. So this is, you have to think of this as a kind of a middle step towards the realization, the implementation of quantum repeaters. Because the quantum memories we need for this protocol could be worse in this sense, right? So if these memories could be worse, definitely this must work than the quantum repeaters, because we need the better memories for quantum repeater. Okay, so I'll show you now how this protocol works. But one thing that I want to say is that Alice and Bob send their state. So what they send is a pulse of state. Okay, it's not that they send a state and then after after this photon reach the quantum memory, Bob send the other one. They send many. Okay, so with some rate, I don't know, depending on the source that they have. Could be megahertz, could be gigahertz. So they send many of these photons from the side too. So you have to imagine kind of a train pulse, okay, of photons around the memories. Once the memories are loaded, okay, so let's say these memories are loaded, okay, fine. Charlie will block the other photons going to the memories and just wait for these other memories to be loaded. So what I'm saying is like you have to imagine as a train pulse of photons arriving at the quantum memories on both sides. Okay, so we have two types of memories. Okay, so the question now you can ask is, okay, but how do we know that the memories has been loaded with the state sent by Alice and Bob? Okay, so how do we know that the photon reached the quantum memory? So we can have two types of memories. We can have heraldic memories, so there must be some internal heraldic mechanism that tell us that these memories have been loaded. Okay, so we send the state reach the memories, and something happened that tell us that we have the storage, or the successful storage of the photons. Or we can have non-heraldic memories. So there is these memories cannot do the cute things, they cannot. There's nothing we can do basically to see that to detect the presence of, not detect actually, to herald the arrival of the photons into the quantum memories. So if these, so basically we can have these two types of memories. So when I did a PhD a long time ago, these memories, heralding memories, which is a type of quantum memories, were very demanding. The coherence time were very small. So we say, okay, let's use not heralding memories. But if they are not heralding, okay, so herald means we don't know if the photon arrives on the memories. How do we know? So we need something, okay, we need something extra, which is basically this Bell state measurement. So if you think about it, okay, so the Bell state measurement, already maybe you know, is basically is perform what is called in a quantum repeater entanglement swapping, right? So let's assume that, for example, I have an EPR pair. So this is a EPR, Podolsky-Rosen pair. I guess you guys already know. So it's an entangled pair, okay, which it could be easily created today in the, for example, with parametric down conversion. So it's something that is in the lab, many labs, you have this type of pairs. So you create these entangled pairs and you send one photon of the pair to the Bell state measurement. Okay, so one photon, I'll show you again. So one photon goes to the Bell state measurement and interfere with the photon sent by Alice. And the other photon goes into the memories. So after this Bell state measurement, if this Bell state measurement is successful, you have that the state sent by Alice will be stored into the quantum memories. Okay, I'm not sure you guys yesterday. I think entanglement swapping, right? That's basically entanglement swapping. Yesterday, I think it was already explained. So that's yeah, an entanglement swapping procedure. Okay. Okay. So the thing is like. This type of setup allows us to store the state sent by Alice into the quantum memories. So, and this is an heralding mechanism. Why it's heralding? Because this beam splitter, this Bell state measurement, you remember, is made by those beam splitter and detectors. So if we get a click from this Bell state measurement, so we hear the click, it means the photon has arrived. To be honest, this is not a full heralding mechanism in the sense that we know that the photon has arrived here, but we assume that the other photons of DPR source is stored into the quantum memories. Again, there could be some inefficiencies and this photon maybe sometimes is not stored, but at least, you know, the main, let's say the main noise, the main source of noise comes from the distance, right? So let's say we have more chances that the photon is from the EPR source is stored into the quantum memories than that these photons reach the Bell state measurement here. And we call this a side Bell state measurement. Okay, so let's call this a side Bell state measurement, and this is the central Bell state measurement. So, okay, this is the way we worked with this type. Okay, so this is ideally that's the EPR pair. Okay, for example, HH plus VV, but you know, in the experimental setup, it's never like that. Okay, so again, this is the same protocol. As you can see, you have there's a side Bell state measurement. You have this EPR. Again, to be successful, you want a click here and a click there. So it works exactly like before, okay? So before, you remember, successful was a click on one of these two and a click on one of these two. Again, this is successful if we get a click in one of these two or one of these two. Now, this is the density matrix given by the EPR pair. Actually, it's plus something else. So this is actually what you create in the lab. You don't create HH plus VV, but you create, you know, some probability that you have the vacuum state, then you have a 1 state, then 2, 3, 4, and so on. This is called multiple emissions, multiple excitations, which are bad. Okay, so this is the setup. Again, I'm going to show you how we can store the state sent by Alice into these memories. That's the goal, okay? How can we do that? So let's assume that Alice has the H photon. The H photon, you remember, you can write as 1010. So that means the photon is traveling in this mode here. Okay, so we want to store the same photon into these two memories. So 1, 0, we want 1, 0 or 0, 1. Anyway, we want something on these memories. How can, using this setup with this EPR and so forth. Okay, so this is just the tensor product. So just look at this side, okay? This is the side that we are interested in. So we have the Alice photon, and then we have these two EPR up and EPR down. Okay, and this is just, if you write the density matrix with this approximation, you will see that, okay, so you have 1 up, 0 down, and then you have this state, which is in the upper mode, and this is in the lower mode, down, okay? It's the same state. Again, from here you can see that, for example, do you remember what I say that we need a click here and a click there? So a click here is given by the photon sent by Alice, okay, and we have a click. And then a click here, for example, is given by these, from if you take these terms and this term. Okay, so as you can see, this yellow of 1, it means that we have 1 photon here, so it will click, will make a click in this detector. So this state in the circle, red circle, will eventually give, it's a successful click pattern, because we have 1 click here and 1 click there. And so we can get this state with this probability into the memory, the state 0, 1. Okay, so it's not the same, this was 1, 0, this is 0, 1, but this is just a convention, of course, right? We can call this 0, 1 as a H state. But as you can see already, we have a storage of this state into these memories. And then if you look at the other terms, for example, if you look at this term, which was 1, 1, right? In this case, this 1 here, so that means you have a 1 in the upper part, this 1 will interfere with so this 1 means 1 photon here, will interfere with the photon sent by Alice. Do you remember when you have a 1 and 1, what happens? What happens is that we have 2 photons here or 2 photons on the other side. So this will give us 2 clicks. And 2 clicks is not allowed. We have 1 click only to be a successful Bell state measurement. Okay, so that's why I put X, because these give us an unsuccessful Bell state measurement. And then this is the other terms, which means a 0 photon on the lower part. So in that case, again, this gives us to an unsuccessful event. Why? Because you have only 1 click. So 1 click, you always have it here because the state sent by Alice. But in this case, if you couple, let's say, if you consider these terms, which is 0, you will not have any click. So again, this is not successful. So at the end, and then that's it. Basically, these are all the terms. So at the end, what I get is this. So as you can see, the only successful click pattern gives us the storage, the successful storage of the photon sent by Alice. Okay, and this is all ideal. I'm not considering any losses here. Okay, there is no channel loss, there is no detection efficiency, nothing, dark counts, nothing. This is all ideal, just to explain you, to show you how the storage works. And the same on the Bob side. I mean, you can do it for fun if you want. Okay, so yes, as I say, this is all ideal. But unfortunately, we do not live in an ideal world, like Alice in Wonderland. But yeah, and so we have to deal with the inefficiencies. So let me show you the rate. So this is the rate that we want to calculate. And the rate is given by, so the rate is, as I said, how fast Alice and Bob can share a key. And you have, it's given basically by this. So this is the, I'll show you. So what are these things? So this is the P click. Is the, basically it's actually the real rate. It's like the probability, I brought it here, is the probability that you have a successful click pattern in the Z basis. Okay, P click Z. And it's given by 2 things, P good and P bad. Okay, so this is the probability, P good, that you have a successful click pattern. This is a probability that you have an unsuccessful click pattern, but we do not know. Because, as I said, when we put some inefficiencies, like dark counts, we might have this unsuccessful click pattern. So this will contribute also to P click. And actually, this is what, okay, so the probabilities are in the Z basis, given by correlated signals. Okay, and then they said that this is probably a successful click pattern in this is given by uncorrelated signals. So that's why P is bad, this contribution. And this is called the quantum bit error rate, or QBER, which is given by, okay, you have the QBER in the two bases, and is given basically by the ratio between P bad and P click. So that's the way to see. So you can calculate, you can find these probabilities, okay, from this QKD protocol, and you find the rate. Let me show you a simple noise model. So what are the noises, right, that contribute to this probability? For example, you have a channel loss, which is modeled by this beam splitter with transmission coefficient eta. And then you have, okay, so that's the way we model channel loss. Then you have a noise in the detector, so that could be, for example, detection efficiency, which is again a beam splitter, and dark counts. Remember dark counts. So as you can see, dark counts, so if you have, let's say, some density matrix, which has the zero vacuum component, right? This density matrix can contain the vacuum component. When we assume having dark counts in the detectors, this vacuum component can contribute, because dark count, as I said, is this thing, right? Is the click. Even if you don't get anything, you get a click. So this is an error, and the DC is just the parameter that describes that. And then we have a noise also in the quantum memories. And the main noise that we look at are there are many, many noises, right? So, for example, one is these multiple photon emissions. So sometimes the memory can emit one photon, but it sometimes can emit two photons or three photons and so on. So this is some type of noise. And the other one is the coherence, which is this apple that from a good apple becomes rotten, okay? That means that the quality of the state, the fidelity of the state stored into the quantum memory undergoes to this type of channel, which is basically, as you can see, it's called a depolarizing channel. So with some probability is still good, but with some probability P is completely mixed state. So all the information has been lost. And these are the main, let's say, the main noises in the quantum memories. So given this noise, basically, this is the special encoding. Basically, this noise, we want to see how the key rate is affected by when we plug this type of noise. And these are some results, just to show you, like what we did. So, for example, when you consider these multiple photon emissions, right, that I showed you before, like 2, 3, 4, so on, this is the probability of the photon emission. And so, okay, so this is the key rate. So finally, you can see the key rate versus the total distance between Alice and Bob for this memory-assisted QKD protocol. And as you can see, we compare here different lines, blue lines, with the red line. The red line is no memory, so the normal MDI QKD. Of course, what we want is that we wished, when we did this calculation, that this blue line cross the red line. Otherwise, we want to show an advantage. But what we find is that when we plug this multiple photon emission, as you can see, we change the values of this P, so 0.2, -2, and so on and so forth, but we never cross the red line. So this shows that when we use memories affected by this type of inefficiency, by this type of noise, we cannot beat the no memory. So that's what it means, is that the protocol is useless then, in this case. But is it really useless? Well, let's see. Let's change memories. So we're still using actually the same type of memories, but this time we managed to create this type of states here. I mean, if you want, I can talk about later if you want to ask. But basically, from these states, what you can see is that, okay, so this state also contains a double photon emission. Can you see you have 2 here, which means you have 2 photons, right? 2, 0, 0, 0, and 0, 0, 2, whatever, which is basically the state coming from this type of module. But what we show is that with this state, we can actually beat the plob, means here is think of this plob as again, the rate of the no-memory system, the highest rate that could be reached. Okay, the blue line is the highest rate that could be reached. And now with this type of a system, as you can see, finally the green line is crossing the blue line. So we were very happy and we wanted to celebrate. But this is just ideal case. Okay, this is everything is ideal here. I forgot about the NLA, that's another protocol, but it's bad. So this is ideal, at least ideal. I mean, when we plug this type of, for example, we have a frequency conversion efficiency, a single photon source efficiency, dark counts, detection efficiency, right? You have to consider all these friends here. So yes, but basically what happened is like, so initially we were very happy, but then when you start doing, using a real existing quantum memories, again, you don't cross it. See, you don't cross, I mean, you cross around here, but it's very low. Okay, that's very disappointing. Okay, and then another type of, so we change again memories, and we're using now NV centers. NV center, again, there's a clear rate, seems like to be better. At least we can cross the green line, but of course this is very strongly affected by the coherence time. And as you can see here, so we just simulate what is the rate. And then as you can see, you can have some advantage, but for coherence time of the order of 100 milliseconds, so it's quite long coherence time. But actually in the NV center, the coherence time of the electron spin is the order of milliseconds. So that's actually not that good. Okay, so and finally, that's the last protocol that I'm going to show you. So as you can see here, the main problem is the coherence time, right? As I said, the coherence time must be high to have an advantage. So actually, the nice thing of NV centers is that we can use both the electron spin and the nuclear spin. And the nuclear spin has much longer coherence time on the order of seconds. So we came out with this other protocol where we exploit the nuclear spin of the NV center. And it's easy. How can we do that? So we do the Bell state measurement, decide the Bell state measurement first with the electron spin, so we can store the state of Alice into the electron spin. Then we move this state into the nuclear spin. And as I say, the coherence time is quite long. So now this electron spin is again free to interact with the state sent by Bob. And that's what happened. So again, you can do the same trick here, do Bell state measurement. And now you have the blue which is the state sent by Alice. And the red state is the state sent by Bob. And basically what you can see here is that, yes, you can see well. As you can see here, the coherence, so the red line, not trapped atoms, yes, this one, the purple line is the single NV center. So the blue line was the previous one. But now, since we are using a higher coherence time, as you can see, we can reach the purple line, we can reach longer distances. And that's all thanks to this, the coherence time of the nuclear spin. Okay, so that was my last slide. So I hope you enjoy the talk. And this is so I mean, I show you how memories, right, can improve the performance of the QKD, especially if you want to do, long distance quantum communication. This is the main way, that's the most important or the most significant method to do. And I show you also, I hope you understood like how this storage process works, and I explain like, the thing is like to find a very good candidate for quantum memories, right? So in our research, we just explored many different memories, and with all these memories, we model the inefficiencies, and eventually we come up with these NV centers exploiting the nuclear spin, because it has very long coherence time, and then the results were quite promising. Okay, so that's the end. Thank you very much. Questions? Yes.
So you gave the example of how on one basis Tara gets split. It doesn't know whether it came from Alice or Bob.
Yes.
But if you put a memory for the clip,
yes,
that parents of Alice or Bob, then surely he knows whether it came from Alice or Bob.
Yes, but you don't know what's the state.
Okay.
of course you know, of course Alice, Charlie know, but still you do not know what's the state sent by Alice and Bob. So these are Bell state measurement, right, that I show you. As I say, that why we say successful. Successful means that, we want something that is successful, but at the same time means that Charlie always knows, let's say, with 50% probability, as I say. Because as I show you, the logic is exactly the same. You have one click here and one click there, right? But you don't know this click where it comes from, right? Because you have this 50-50 beam splitter. So I can show you the other in the board. Like this 50-50 splitter basically, cancel, as I said before, from where the photons come from, right? Because when you have a 50-50, the photon can be reflected or could be transmitted with 50% probability. So here the thing is like true. Yeah, of course, Charlie must know if Bob or Alice, but still don't know what's the state stored. Yeah.
So usually at the centers we use electrons to detect the nuclear. We cannot directly, to my knowledge, directly influence the nuclear spin, and we cannot take the readout from the nuclear spin directly from a user.
No, so we can. So what we can do, at least what we did it before, was to transfer the state of the electron spin into the nuclear spin. And then there is an interaction, a hyperfine interaction, electron spin and nuclear spin. And thanks to this interaction, we can basically perform a Bell state measurement, which is basically the middle Bell state measurement that I explained before. So thanks to this interaction, right, this coupling between electron spin and nuclear spin, we could perform the Bell state measurement that correlate the state of Alice and Bob, right? That's eventually what we want. Any other questions?
Okay, there's no more questions. Let's thank the speaker again.